Hello, this is Saabirah and I will be conducting the final presentation for the Data 670 Capstone project. So here's the agenda. Firstly, there will be a brief overview of the project, the scope, and the importance. Then we'll discuss some of the success factors and then move on to the data preparation and cleansing. Next, we're going to move on to the methods of data analysis, starting off by looking at the descriptive analytics and visualizations, moving on to the predictive analytics and models development, and then finishing off with the findings and insights gained and the conclusions made. The key objective of this project is to understand how the data analysis is used to create the predictive models and the results produced by these models. The main business problem is that rent prices impact the renters as well as the landlords. Renters are affected in terms of costs and planning of expenses, while landlords require the knowledge to be able to properly plan out their income streams. Key task of the project is to make use of machine learning models to make accurate predictions of rents to be charged on different types of houses. The flaw with the traditional rent determination system is that socio-economic factors such as employment rates, unemployment rates, household incomes, and ethnic mix are all ignored. This project incorporates these variables to produce comprehensive results. There is a shortage of affordable housing in the US, so it is key that rent prediction is done accurately in order to enable ease of access to rental housing for as many people as possible. Further, the property market is a key indicator and driver of the economic health. Prices will be affected based on the people's access to housing and its affordability. Next, we move on to the project scope. Of the different listings provided, there are 12 different types of housing, namely apartments, condominiums, townhouses, assisted living facilities, cottages or cabins, duplexes, flats, houses, in-law properties, lands, lofts, and manufactured properties. Units range in size from 188 square feet to 1,687 square feet. Listings are sourced from all 50 states in the US. The listings also highlight the different features and facilities available in each property. The data for the listings was sourced from Craigslist but was obtained as a CSV file from Kaggle. The census data, which will be supplementing the primary dataset with the socioeconomic variables, was sourced from the US Census Bureau but obtained as a compiled CSV file from Kaggle. The target variable of the project is the monthly rent in US dollars on a unit of housing. The key success factor is to incorporate the knowledge gained from the previous courses in the MSDA program to deliver a well-rounded capstone project. Additionally, success factors for each stage in the project are defined below. Firstly comes the selection of data, and this involves justifying the choice of datasets, exploratory data analysis, and a plan to combine the datasets for usage. Next, in the data pre-processing stage, it involves description of the tools to be used, explanation of all the cleaning and processing activities done, the feature creation, and documenting of the rationale. In the descriptive analytics stage, it involves creation of visualizations in Tableau and the documentation of the insights provided by those visualizations. Next, in the predictive analytics stage, it involves building and comparing multiple predictive models, assessment of important predictors, and a clear recommendation of the champion model to be made. Finally, it involves documenting all the results from the entire project into a final report. This should enable the data analyst to be able to tell the story effectively and communicate the results well to the decision makers and stakeholders. Insights and conclusions need to be highlighted. The main dataset is the house listings dataset from Craigslist. Its key features include the target variable rent, the housing type, size, number of bedrooms and bathrooms, the availability of different features and facilities, and the state where it's located. The secondary dataset is the census data from the US Census Bureau. A few socioeconomic variables such as poverty rate, median incomes, employment figures, unemployment rates, and ethnic mix were chosen to supplement the main dataset. Combining datasets was done using an inner join approach to link them using the common state variable. This was done using the DB2 service in the IBM Cloud Platform. Data preparation activities were then carried out. Missing interval variables were imputed with the mean value, while missing categorical variables were imputed with the modal value. Only variables that add value to the analysis were included, and redundant variables were eliminated. Variables with complex titles were renamed appropriately and according to a convenient format. Besides the target variable, the number of predictors was minimized and finalized to 28. These predictors include the three newly created features as well. The new variables are firstly, employment rate. This is the conversion of absolute numbers of employed people to a percentage. Secondly, the annual median household income variable was divided by 12 to obtain the monthly median household income. Finally, the monthly post-rent income was found by deducting the monthly rent charge from the monthly median household income. Next up, in the descriptive analytics section, are the visualizations. These were created in Tableau. Firstly, a map to show average rent costs in each state, filtered by the type of housing, was created. Secondly, a map to show the post-rent monthly income in each state was created. Higher the post-rent monthly income, greater the value for money offered by a state. A scatter plot to show the correlation between average monthly incomes and rents, filtered by unit type in each state, was created. The strength of the correlations can be judged by looking at the R-squared and p-values. Shown here is the average monthly rent in each state, filtered by the unit type. The darker the shade, the higher the average rent in a state. This enables filtering the results by housing type. The overall average rent, considering all the unit types, ranges from $719 to $1,641.4 per month, where Hawaii was the most expensive state and Kansas was the cheapest. The other expensive states include California, Massachusetts, and Colorado. The map varies according to the applied filters, and the ranges of value vary as well. The next visualization shows the average post-rent monthly income in each state, along with the average monthly rent and the total average monthly median income. Results can be filtered by the type of housing. Darker the shade, greater the value for money offered by a state. Depending on the housing option type selected, the map will change and the averages shown will differ. The overall average post-rent income, when you consider all the unit types, ranges from $2,298 to $4,940 per month. Connecticut offered the greatest value for money, while Mississippi offered the least. Alaska seems to be another state offering quite a bit of value for money, since it's more darker colored. The results vary according to the applied filters and the ranges of values as well. The scatter plot shows the correlation between average monthly incomes and the rents for each state. Each point represents a location. The variables used to create this plot were the average of the rent variable and the average of the monthly median income variable. The option to filter by the property type is also available. When the all option is ticked, the overall correlation is shown by including housing units of all types into the analysis. Depending on the selected option, the plot will change and relationships shown may differ. The trend line is the line of best fit, and hovering over it will display the equation of the line based on the applied filters, along with the R-squared value and the p-value. These two values help to determine the strength of the correlation. We then move on to the predictive models which were built using SAS Enterprise Miner. We built linear regression models, a random forest model, a neural network model, bagging and gradient boosting models, and finally a heterogeneous ensemble model. The target variable is the monthly rent, which is an interval variable and has no imbalances. The process flow diagram of the models built in SAS Enterprise Miner is shown below. The focus is on building accurate models, and the key is to predict rent accurately. Therefore, a trade-off between accuracy and interpretability is expected. Simple models are easy to explain, but complex models are generally more accurate. So what was done in this project was to build a mix of simple and complex models, and the comparisons were made appropriately. The first model built was the linear regression models, and these are very simple models. 4 different versions of the linear regression model were built. These 4 different versions were based on the different variable selection methods. The selection criteria for the best of the linear regression models was to pick a model that had the lower ASE and RASE. Lower the ASE or RASE, better the model performance. The stepwise variable selection model had the lowest ASE on the validation and training data, and therefore it was the best regression model. Models which incorporated all the variables and the backward selection model had the worst performance. They had the highest ASE values for the training and the validation datasets of all 4 models. The worst models displayed overfitting, but the stepwise and forward selection models did not. Next up is the neural network model. It was the second best model after the linear regression model. However, the performance differs drastically. There's a big gap difference between the performance of the linear regression and the neural network models. Again, the selection criteria was based on the ASE and RASE. Lower the ASE or RASE, the better the model performance. Shown on the slide are the ASE on the training and validation datasets. There was no model overfitting, and over 40 iterations were required to reach convergence. Then came the random forest models. It turned out to be one of the poorly performing models. Again, the selection criteria was the ASE and RASE. Shown are the ASE on the training and validation datasets. Since the validation datasets ASE was higher than the ASE on the training dataset, there is a slight indication of the presence of model overfitting. The random forest model also shows rankings of the predictor variables based on different factors. Next up is the gradient boosting model. Again, this was one of the poorly performing models. Selection criteria was again ASE and RASE, and the ASE on training data and ASE on validation data are shown on the slide. There was no model overfitting for the validation set. ASE was not higher than that of the ASE on the training set. The ranking of independent variables by importance is shown in the bottom image. Unimportant variables were not included in the list. State seems to be the most important variable. Finally comes the bagging model. It's the poorest performing model of the lot, and again the selection criteria was the ASE and RASE. ASE on the training and validation datasets are shown on the slide, and there seems to be presence of model overfitting for the validation set. ASE is higher than that of the training set. Finally, a heterogeneous ensemble model was created. This was built using a combination of the neural network, all the 4 regression models, and the gradient boosting model. So there is a diverse mix of the models combined to create this ensemble model. Performance-wise, this was the third best model. The selection criteria was the ASE and RASE. Lower the ASE or RASE, the better the performance of the model. The ASE on the training and validation datasets is shown on the slide. There was no model overfitting for the validation set. ASE was not higher than that of the training set. The heterogeneous ensemble model was built based on the average method. Finally, the champion model is the stepwise linear regression model. It's the best of the 4 linear regression models and the overall best model, since it has the lowest ASE and RASE of all the models built so far. It does not overfit. It generalizes well to new unseen data. Regression models are one of the easiest and the quickest to train, and it even outperforms more complex models despite being a simple model. More complex models, which are expected to deliver more accurate results, fail to do so, and a simple model such as the linear regression model built based on the stepwise variable selection method uh, outperformed such complex models. We then move on to the conclusions derived from the predictive models building. The champion model for the capstone study was the stepwise linear regression model, as identified previously. It had the lowest AAC on the validation and the training data. Regression models are one of the easiest models to interpret, since the equation is based on a mathematical formula. A model highly accurate, the stepwise linear regression model is both highly accurate and interpretable. It delivers a good result with no major trade-off. The second best model built so far was the neural network model, and the goal of the project was to predict rent of different housing units. Predictions were made by dividing the existing dataset into training set, validation set, and the test set. Training data comprised of 50% of the overall dataset, validation comprised of 30%, and test set comprised of 20%. Models were built based on the training data. The results were evaluated using the validation data, and the test set data was used for testing performance of models on unseen new data. Finally, a review of the key KPIs and results can be looked at. Of the quantifiable insights, the most expensive states on average in terms of rent, states offering the most value for money, and correlations between rent and monthly incomes via descriptive analytics and effective visualizations was performed. In the predictive models development, we identified that models must be able to predict the rent to the dollar for each house listing. This was the goal of the project. Rent was an interval target variable, so no biased target variable problem. No adjustments needed to be made. And the results obtained from the predictive models development showed that the champion model would be the model with the very low ASE. The champion model is both highly accurate and easy to interpret, which was the case for the stepwise linear regression model, and there were clear correlations of specific variables and the rent. Findings on factors showed that the few predictors were key to determining the rent. The stepwise model identifies this, since it only identifies that 5 specific predictor variables prove to be the greatest contributors towards prediction of rent accurately. Specific combinations of factors contribute to the rent determination. As for recommendations on future analysis, it would be great if we could include a broader range of locations beyond the USA and on a global perspective. Taking housing listing data from an international range of locations would provide a greater target area to be explored. Alternatively, it would be possible to drill down into the region-wise or county-wise level rather than just the state, for state is a broad area. Additional predictive models which were not covered in this study could also be built. Rents are not accounted for the time value of money. These were ignored. Accounting for them would make the predictions more realistic and useful. Thank you.